Let's bring it in for class.
Should I do the table bang?
Yeah, you can bang the table if you want. My marker's starting to run out of. I think I gotta use my other one.
Yeah. Wait, you didn't do the language of the day.
I know, I forgot. I had Greek homework. Unfortunately. Okay. Imagine doing that in the 8 a.m. health class. Okay. Beverly, do you want to pray us into today?
Thank you, Lord, for everything that we studied this seriously. So much for the chapel, and that we get to gather here and learn the numbers that you gave to us. Thank you, Lord, for understanding and for diligence. Really, thank you.
Okay. Well, we're gonna do today a little bit different. Hi, Chelsea, how's it going? Due dates. What's due tonight?
Last one.
Good. So that means turn it in. Just to establish an expectation, tonight this won't usually be the case, but I will be sitting up because I have work myself, so I'll be up late. So once the due date passes and I finish and clean up my homework, I'm gonna go to the Dropbox and I'll look through, and anyone who hasn't put it in, I'll make my life easier and just drop zeros, and I'll do those first. A zero is a reminder, okay? So zero is not permanent. If you see a zero in your gradebook, that means, hey, guess what you forgot to do? Please put it in the Dropbox. Does not mean that I can't change it, okay? So I am very, very willing to, on a case-by-case basis, deal with extensions and stuff. But it is not the expectation necessarily. So you don't want zeros to sit in your gradebook. You will lose, I think I did the math on it, you'll lose 2 percentage points off of your overall class grade as a whole for each one. It's probably not a good idea because you'll need all your points you need for your exams. Again, it's not supposed to be accuracy based. So I don't want you guys to be sweating, right? When you're solving the questions, you're like, I just don't know if this is right. That's okay. Just have what you have, move on, keep going, okay? Especially when it starts to get closer to the due date. If there's stuff that is just like, I don't know. So here's what I can do. This is what it's gonna be. And if you need to get it done, just keep moving, okay? The idea is I don't want stalling to happen. Whenever stalling happens in math, you just get behind and it's really bad. Because that's gonna start piling up, and that should not be piling up in the first like 4 weeks of school. So make sure it's in, doesn't have to be completely correct. Obviously do your best, but think of it as exam prep. Labs are exam prep designed to pad your grade, okay? So don't let the thing supposed to pad your grade be the reason it goes down. Okay, that'd be slightly ironic, okay? So yes, will I assign zeros? Yes. Will I be happy to assign zeros? No. Just don't make me do it, okay? It's my least favorite part of my job. Yes. Do you have a question? Okay. Okay, so the calendar has been a little bit messed up by ORU in general. So here's how it's gonna happen. Okay, today we're gonna cover 14.3. And so tomorrow is then Saturday, then Sunday, and then Monday is Labor Day. No classes on Labor Day. And then there's Dr. Harder. On Tuesdays, you'll give lecture again after Labor Day. Wednesday, we'll also go over a lecture. And then by the time we get to Friday, we should be able to cover everything that's going to be on the first exam. Because then after that weekend, you'll study for the exam. And then that first exam is going to be the Tuesday that comes right before fall revival on the 13th. So the exam, I'll just so that you have it, you can write this down. Exam 1 is on September 12th now, because September 13th is Wednesday. So that's a Tuesday. That's when the first exam is going to be. And so the idea is, since that's when the first exam is, I need to make sure you've seen everything before that week, especially before Monday. So the Monday before this will be an exam review day in class. And then the Friday before, we'll cover, because the calendar says that we're covering the topic, then I thought, well, that's probably not enough time to turn it around. So basically, where it says test review on the calendar and curvature and normal vectors, those will just switch spots. So that way you have a weekend to see everything, practice, and then exam review. Make sense? Okay. So that's just going to correct a slight oversight in terms of the logistics of getting through the content. So today is not too bad though, because it's really just rehashing all the stuff you're familiar with in AP calculus, if you took that, or Calc 1 applications in physics. Oh, clear it is. And then actually, you know what we'll do this because you have a whole extra day, Labor Day. Try to finish the rest of Jonah. And then I'll be calling on some of you guys to share. Because I think especially heading into exam season, that story is going to be kind of appropriate for you to do that. So do not shirk and run away from your responsibilities that God has given you.
Why not?
Well, you can get eaten by a fish. That could be fun. There's other things. Why does it just say Tuesday?
I don't know.
Okay.
Guys,
So 14.3 is going to be all things, this is gonna be all things, physical applications now of vector value function, okay? So let's start with the definitions. Did I choose the wrong marker again?
Heard that.
Okay, so position, there we go. Okay, position, this is gonna function equivalently to just how we have a regular function in Calc 1. So instead of using X, we'll use R. Well, actually in Calc 1, you probably use S for position. So we're just gonna use R of T. And now we parameterize X of T, Y of T, and Z of T. And since it's a physical application, we're starting with non-negative time. We have non-negative time. And so velocity is nothing crazy. We just take the first derivative. So velocity demarcated with the V. Notice that these are vector value functions, so that's like the vector there, and these are components, so those are not vectors. So V of T is R prime of T, right? So that's nothing crazy. And so if we wanted to see what those components would look like, that's X prime of T, Y prime of T, Z prime of T. All good? And then so there's position, velocity, and acceleration. Those are kind of the little, I don't know, they go together as the trio for the main applications in physics at least. And that's going to be derivative of velocity, right? So you could think of it as the second derivative of your position vector value function. That's okay. It's X prime prime, Y prime prime, Z prime prime. So nothing new, nothing crazy. We're just reminding ourselves that these relationships that existed in Calc 1 are still, they're pertinent. Now there's one difference that is actually going to be relevant, because now that we have vectors which have both, the magnitude and a direction, is that when you think of velocity, that's describing both not only how fast you're going, but which direction you're going in. Whereas speed, if you look at a speedometer, is your speedometer telling you whether you're going east, north, or south? No, it's just telling you what?
Speed, scalar.
Regardless of your direction. And so we do have a way to talk about this now with these vectors. So speed is going to be defined differently than velocity, and we'll treat them differently. So speed
Is it scalar?
right, so it's scalar quantity. So we think of speed as being simply just the magnitude portion of the velocity, right? Speed isn't the direction, speed is the magnitude of the velocity. So magnitude of the velocity. And then simply apply the definition of magnitude of the vector to that. So regardless of what these components are, we can always plug that in. So square root, the big overall square root, and we'll take X prime of T and we'll square that. We'll take Y prime of T, that next component, square that, take the third component, which is Z prime of T, and square that. So is speed the same thing as velocity?
No.
No. do we derive speed from velocity or velocity from speed?
Speed from velocity.
Good, so that's the relationship. So if you remember that, you're pretty much golden, okay? There you go, that summarizes an entire section, because now the number of applications are infinite. The moment, now you can just start sticking in, functions that are differentiable into here, and then all of that calculus stuff comes back, it's all the same. Granted, you're doing it now with like 3 different parameters, that's fine. And the only thing that's different is speed, so calculating speeds is now actually going to be really to something else. Now, speed doesn't have to necessarily just give a number out, so you can describe speed as a scalar valued function. So right now it's being presented as a scalar valued function, because I haven't selected a specific value of t yet. So there will be a slight difference in saying, hey, find the speed at time t naught versus just find the function that describes the speed. So if you want the function that describes the speed, just do this without actually substituting anything specific in. And then if it wants it at a specific point, then go ahead and plug in check. Does that make sense? So nothing should be different from what you're familiar with already in Calc 1. Okay, so there's different kinds of position functions, and we'll talk about the main ones that the textbook wants you to know, at least in this class, is uniform motion and circular motion. And the circular motion is actually pretty fun. So we'll be good to erase. And if not, I guess that's motivation to read the textbook, because the textbook's got all of this and more. Oh, as a general rule of thumb, textbook problems and doing the Pearson homework and the lab, it's pretty much a surefire bet for exam prep. This is not a 400 level math class, so it's not going to be sprung upon you to solve some random thing you've never taught. Yeah.
So you said Pearson and the labs?
Right. And the textbook. So if you go through the textbook and you work through those examples too, those are the ideas that you'll be tested on. You won't be given some completely random new, thing to deal with. Dr. Lang did that to us once last semester. That was terrifying. So if you think this isn't fair, he put a question on there involving a definition and concepts we never were taught in class. So we had about 15 minutes in the exam time to figure out the concept, then solve the problem on this new concept. So that's some math major stuff, but we don't do that in engineering Calc 3. It's lots of algorithms, lots of just practicing procedures. Okay, so uniform, sometimes we call this constant velocity, which is an indication of what the velocity vector is going to be. So constant velocity. And then straight line motion, right? So this is what we refer to either uniform, constant velocity, or straight line motion. And it's actually going to be a familiar face from previous sections. X naught plus AT, Y naught plus BT, and Z naught plus CT. So in other words, it's just the equation of a line. The only difference is that with motion, again, we just want non-negative time. Does this look familiar from the equation of lines? What's the direction vector? If you were to strip that out, what's the direction vector of this line?
AT, BT, CT.
Right, so it wouldn't include the t, but it's the things that are multiplied, all the coefficients of t. So the direction, the coefficients is, well, that's going to be misleading. I'll just say the direction vector is the coefficients of the variable. Now, actually, this is interesting because what's the first derivative? So what's the velocity of this?
A, B, C.
Yeah, A, B, C. Oh, interesting. Its velocity is its direction. And considering the way a line works, wouldn't we hope that the tangent vector to a line is basically the line itself?
Yeah.
It's common sense. It's not like we're not doing Newtonian mechanics here. We're just using common sense. So this is linear motion. It's going to move on line. You already know this. Now, what you don't really know yet is the circular motion stuff. So circular motion circular motion is going to have a base position vector of now usually we do it like this. So rho is going to be the radius. So rho cosine t, rho sine t. And then we'll do this in just 2 dimensions for now. You could extend this by just putting a constant there. And then that's going to go, who knows what the parameter is? So we 0 to what? Now we could, we don't have to necessarily do exactly 0 to 2 pi every time, but if we just want the standard trace out one circle once, that's what we do. If you wanted to trace out a circle 4 times, what does that need to be?
8 pi.
Good, right? Because we multiply our 2 pi radians by 4, the 8 pi. If we only wanted to go around 1.5 times, what would we do here?
3 pi.
Yeah, 3. Good. Okay. I might do on exam review day, I might do a unit circle review. Because that's almost always pertinent regardless of the level of the math class. Okay, so we'll make a few observations here because this is really interesting stuff. The velocity is going to be what?
Negative sine.
Right, minus rho sine t. And then the good. And let's see, yeah, so 0. And then the acceleration is going to be what?
Negative rho cosine t.
And then
Sine.
yeah, minus, because cosine is gonna go to minus, so
Minus
minus rho sine t. Rho t. You might think, why does Scott rewrite that every single time?
Which is important.
Yeah, that's important. The moment I omit that, I'm assuming minus infinity to infinity. That's very different than 0 to 2 pi. Okay. Okay, now this might, since this is the first time you're seeing this, you might not really get this, but if I were to take the dot product of R with V, right? So if I were to take R and take the dot product with V, I'm taking rho cosine t and minus rho sine t, and that's giving me minus rho squared sine t cosine t, right? Now, then I do it with the y coordinate. So the rho sine t times rho cosine t give me rho squared sine t cosine t. Interesting. So these are going to cancel. And we get that the dot product R dot V is actually just a 0. Now, if a dot product is equal to 0, what does that indicate about the vectors involved in the dot product? Orthogonal. Ah, interesting. And is it really all that surprising that the first derivative, which is the first derivative velocity was called, who remembers what we called that specific vector last class? When you take the first one. Yes, the tangent vector. And tangent vector to tangent to a surface that's going to be, especially on a circle, is going to be orthogonal. So I'll draw a picture after we do these dot products so you can see it. And then also with the velocity dot acceleration, what do you think that's going to be? Yep, just 0. Because now this is the positive rho squared sine cosine, and then this is negative rho squared sine cosine. So again, you end up with this. Additionally, what's the relationship between the acceleration and the position?
The signs are switched.
Yeah, so acceleration, when you're moving along a circle, is actually just the opposite direction of your position. So I don't know if you're physics people, you probably talked about centripetal acceleration. The calculus in itself verifies this even without considerations to the physical parameters, which is pretty cool. So thumbs up if all this is good, because I'm going to move to just, I'm going to draw out the circle thing so you can see all the pieces working together. I think I'll leave this up right here, since this is what we're gonna be illustrating, the dot products and those different properties we got from the circle. Notice that this is not for a line, like, so that would not be true if you just got a line. This is only true for circles. And what's kind of interesting is this is gonna actually extend into 3 dimensions, regardless of what circle we're using. So I'll do a 3-dimensional circle here. So if we've got there's an X, there's a Y, well, sorry, I should specify a circle that is existing inside of 3 dimensions. So it doesn't have to be restricted to a plane. Okay, so we could have some sort of circle not restricted to a plane, but it's kind of slanted out, right? So try to picture the 3 dimensions here. And so the position vector is by definition going to start at the origin and then go up to trace out where that is. So when we talk about this specific point on the circle in the vector, that's really the position vector that's happening. It's the vector that's going from there and its head is ending at that point. So this is like our vector arm, right? It's our position. And so then as this is moving, so you can imagine if you ever taken your keys on a fob and you just kind of swing it around. So as it's moving, its velocity is going to change instantaneously. That's why we have an acceleration. But if we froze time at that moment, the velocity is indicating tangent, right? So we're along slope of this, so it's going to be coming down. So this is our velocity. And that is always moving orthogonally. And so there is our r dot v always equal to 0 on a circle. So in circular motion, if we're swinging this around. Everyone see that? So we got that tangent vector. And then we have our centripetal acceleration. So we're told that acceleration is actually just going to be the negative version of r, which means it's the same vector. We just flipped it around. So it's going from the point back down. That's how it's accelerating. So its position is going there. It's orthogonally, the velocity is orthogonal to it, and then it's accelerating exactly back from the point to the very center. Centripetal acceleration derives from understanding dot products. And it's pretty cool. Okay, any questions about that? Or is this pretty much straightforward? More or less. You'll convince yourself more when you go to the Pearson and interact with some of these. Sometimes what they'll do is they'll take a sphere and then they'll like restrict a trace on that sphere, and then that's the circle you're working with. But we can move on to the more difficult portion of this, which is the I don't want to call it a differential equations problem, but that's really all it is. In physical application of throwing objects through a gravitational field that moves in only one direction. So this will be a slightly more sophisticated understanding of the previous model we usually set up in Cup 1, but it's still pretty restrictive because we're treating gravity pretty naively. But here, I'll paint you a scenario. So here is kind of a 2-dimensional plane. And here is the X, here's the Y. And we need a position, we need an initial position to start. So this vector R is going to indicate this point as being the initial position of our object. And so this will be the initial position. And it'll be r of 0, right? Because time is equal to 0 initially. And we'll call this x naught and y naught. I know that's a little bit small. Can everyone see that okay? Okay. And then what's going to happen is we have this initial position. So it'd be like if I was holding a ball and then I decide to then from here throw it with some specific initial velocity. So then the initial velocity, and then it's going to come flying through the air. Okay, so this is the trajectory of the ball. And specifically, that initial velocity is not necessarily the trajectory, but it's tangent to the trajectory immediately after the release. So this is that initial velocity. initial velocity. And we can call that, there's lots of different ways to label this. The textbook calls it V of 0, and they're going to label it as U naught and V naught. I would personally have just called it Vx and Vy because that's more mechanics art. U naught and V naught, that's what they're using here. It doesn't really matter. It's just constant.
That's a U and what?
A U naught and a V naught. Yeah. Now, overall, so in this entire situation here, there is an overall downward force, right? And this force is gravity. So gravity is F. And we can just use mg, which in itself is a relatively sacrilegious approximation anyways, but for the function of what we need to do for motion in this application, that's going to be fine. Okay, all good? This is the problem. This is the setup. And we're going to look and describe what the original position function is going to be, because we can describe every single one of those positions working backwards just from the second law. So we start, what's the second one? Here? Minus mg, so from physics. Yeah.
Do you not like negative mg?
So we have ma. And now notice that instead of just ma the scalar, it's ma a vector value function. So ma is equal to f. And that is 0 minus mg. And so if we divide through by m, we're left with the equation. Acceleration is 0 and then minus g. So from this and our the initial condition of velocity and initial position, we can actually figure out and work our way backwards to the position. So we integrate. And if we integrate, that's the velocity. So velocity is integral antiderivative, that is, of acceleration. And when I perform that integration, right, we get integral of this vector 0 minus g dt. And from when we talked about this, I think on Wednesday, we can just anti-differentiate as we go. So this will be 0, this will be minus gt. And then we don't want to forget our arbitrary constants, right? So I'll show this C1, C2. So arbitrary constants. And now once we have arbitrary constants, that's where we plug in the initial condition. So v, when t is equal to 0, that's what we can expect. So when t is equal to 0, we can expect to have u naught, v naught. Then we're going to plug in t equals 0 everywhere over here. So that's going to leave us with 0 minus g times 0 is what? 0, right? So 0. And then plus C1, C2. So the conclusion is simply, okay, the C1 and the C2 were just zeros. So we can use U naught and V naught as the arbitrary constant. Make sense? That's like saying, that would be like saying 5 is equal to 0 plus 5. In this case, we just have vector is equal to 0 vector plus another vector, they're the same. When we plug this back in, we'll get that the velocity is 0 minus gt plus u naught v naught. And then if you wanted to simplify that, you can just combine it and make it simpler. So velocity is u naught and then v naught minus gt. Are we all good up to here? So this is just what you do in Calc 1. And then now we're at the velocity. So we're going to repeat the entire process over again, just to get down to the position. So position R is going to be integral v t dt. And so you can plug that in, the integral u naught, v naught minus gt dt. Now when we anti-differentiate, we have something a little bit more interesting. What's the antiderivative of the constant u naught?
ut.
Yep, u naught t. And then what about v naught? V naught t. And then minus GT, what's the antiderivative of that?
Minus GT squared.
Raise the power of t by 1 and then divide by that.
Negative 1/2 GT squared.
Yeah, so g halves t squared. And then don't forget your plus c. Okay, and you can check this. I honestly find it easier to differentiate than integrate. So whenever I anti-differentiate, I mentally double check my antiderivatives just to make sure. Because I can easily take the derivatives of my guesses and then see if it lines up with what it should be. So this 2 will drop down, cancel with that 2, I'll get minus GT, it's perfect. Okay. And then again, how do we get rid of the arbitrary constant? Yes. So we'll set t equal to 0, and when we set t equal to 0, we expect to have our initial position x naught, y naught, as designated here. What's u naught times 0?
Yeah, 0.
And then what's v naught times 0?
0.
What's g halves times 0 squared?
0.
Very difficult. Yeah. And then C1, C2. So then in this case, C1, C2 is actually just the same thing as your initial. So the overall position can be described as U naught T V naught T minus G halves T squared plus that constant, which is just the initial position X naught, Y naught. So if you wanted to combine this into one equation, I'll do it up here. So kind of this is the whole reason we did this. That position is X naught, the initial, so your initial X coordinate plus the initial velocity in the X direction times T. And then the initial Y coordinate plus the initial Y component of the velocity times T minus, then we factor gravity, and the minus G halves T squared. And this right here tells you this is the position of an object thrown in gravitational field with initial position given by the numbers x naught, y naught, and initial velocity u naught, v naught. So now you know the calculus 3 behind t-shirt cannons in the Maybe Center. Questions about this? Let me rephrase that. If I were to erase this, and if you had an exam right now where you had to solve this question and get to the correct final answer, you'd all have 100%? Okay, so in that case, what I'm going to do is I'm going to erase the board. It's 1:36 right now, so you get to be dismissed when you're able to come up here having worked this entire thing out on your own, fresh sheet of paper, okay? Because if you're able to do that, the rest part, no, you don't get to see this, you're supposed to figure it out. Because if you're able to understand how to set that up, and then do the calculus 1 mechanics, you can do it in 3 dimensions, and then you can pretty much generate the rest. We have the initial, yeah, I'll get you some initial stuff. So here's the initial stuff. So you'll find the position function. And you're gonna want, that's gonna be R. You're given that acceleration is going to be just strictly going down, right? So minus G. And you'll be given that the initial velocity is U naught, V naught, and also that the initial position, because you will need to know that, is X naught, Y naught. I was gonna show you some other formulas from the section, but then I realized if you can actually just do this, then you have pretty much the capacity to know what those formulas are. Considering you never actually really use the formulas, all the applications are you setting up the problems from that ends up resulting in the formulas. But if you can't even set it up, then the formula is just a waste of your time. So there's the problem. You are dismissed when you can bring up a solution that gets to the final answer.